Hello everyone, welcome to Data Science course brought to you by NM. So in this series, what we're gonna do is we are gonna cover all the aspects required for data science, covering basic mathematics, linear algebra, statistics, machine learning, and even probabilities, and many more artificial intelligence as well. So let's start from the basic. As we all know, mathematics is the base foundation of machine learning. Without math, it is nothing. Machine learning or data science is nothing. So we have to go through some of the basic and important aspects of mathematics that has been required for data science. So in this series, we are going to cover a lot about linear algebra. And in this video, we are going to cover about vectors and how vectors perform, what are row vectors, what manipulations can be done in vectors, and the mathematics behind it. Points and vectors are one of the basic concepts and yet the important concepts of linear algebra, which have a great aspect on machine learning as well. So let me make you understand using the simple coordinate geometry that we must have learned in our previous grades on what is vectors and what is the base of the vectors and how our simple mathematics can help us to understand it. So now let's take, I have two axes or two coordinate geometry, x-axis and y-axis, and I have a point or A over there. So now I want to know the distance of that point A from the origin. So how do I calculate that? So I have two axes and this is a 2D coordinate system. So this point A will represent two values. So what are these two values? The first value determines at what distance is my point from my x-axis, and the second value will determine what distance is my point from the y-axis. So this is how I represent a point. So a point is been represented as a vector in those square braces. So I write my P as a two-dimensional vector where 2 and 3 are the components of it. To represent a point in three-dimensional space, how can I do it? So I will have this three axis. Let me draw the three axis. So x, y, and z. This is a 3D coordinate system. Okay, and let's assume I have a point over here, and this will hold three values: the x-axis value, y-axis value, and z-axis value. So the vector that I will be getting will have three components: x component, y component, and z component. So this is a vector form of it. So the next immediate question that you guys must be getting is, okay, we got the conclusion from the two-dimensional point and also from the three-dimensional point. Yeah, we can draw it onto the surface or something, but what about the n dimensions? We can't represent it using a pencils or using a computer system. So that's where the vectors come along. It uses the same mechanism. So if there are n points, the row vector will have those n components. Mathematically, we can write n dimension points in n dimension space. So now let's discuss on the points let's discuss on the distance of a point from a particular origin. Okay, now let's draw a 2D system, 2D coordinate system. Most of the vectors problems will be discussed using the 2D coordinate system, then later on 3D coordinate system, and then we will move to higher dimensions. So I have x-axis and y-axis and a point P over here containing two values A and B. So I want to find a distance of P from the origin. So as you can see, A is nothing but the distance from y-axis to the point, and B is nothing but the distance of x-axis to the point. Okay, so if we use a normal Pythagoras theorem that we learned in our previous grades, we can easily determine the distance of the point from the origin. So the D is equal to under root of a square plus b square. That's how we get the distance of a point from the origin just by using the Pythagoras theorem. So now when we apply the same thing that we applied in two-dimensional space to three-dimensional space, what we have to do is just add the another component. For example, in three-dimensional space, the formula for distance for a point will be under root of a square plus b square plus c square, and that's it. So now moving on to the n dimension space, it won't change that much. it will simply be the n components. So distance will be nothing but under root of a square plus b square plus c square up till n square. That n represents the components of it. So now let's discuss upon to find the distance between 2 points using 2D and 3-dimensional coordinate spaces. So let me draw the axis for you. One I will be making is x-axis and y-axis. This is x-axis, okay, and we are having a point A over here and B over here. So now what I need is to find the distance between 2 points, that is D. So now let me draw the perpendicular from A to the x-axis. This is nothing but the distance from the origin to the point A, and same for B, and draw the perpendicular from y-axis to A and B. As they are perpendicular to each other, A1 and A2 are the first components for point B and A respectively. Similarly, B1 and B2 are the second components of the points B and A. So point A is nothing but A2, B2, while point B is A1, B1. To get the distance from A1 to A2, what I need to do intuitively is just subtract A1 from A2. Similarly, to get the distance from B1 to B2, what I just need to do is just do the subtraction of B2 minus B1. So we got the distance. Now all we just need to do is put the pieces together and use Pythagoras theorem on it. So D is equal to under root of A2 minus A1 the whole square plus B2 minus B1 the whole square. Now if we follow the same methodology for 3-dimensional space, the distance for the 3-dimensional vector space will be D is equal to under root of A2 minus A1 the whole square plus B2 minus B1 the whole square plus C2 minus C1 the whole square. There will be 3 components in 3-dimensional vector space. So now we have got the base clear about the theoretical concepts, right? We know what the vectors are, the base of the vectors, then how do we implement that vectors theoretically. So now let's move on to practical aspects. Let's get our hands dirty. So before moving on, let me tell you, or let me introduce you to this platform. This is known as S2 platform. It is brought to you by NM, and believe me or not, it is one of the amazing platform. It just not only supports the notebooks but also consoles and other markups and terminals. And let me get you familiar with this portal. Okay, so basically this portal consists of just like a normal IDEs, but the extensive part is we have the S2 library as well. In that we have brilliant and amazing math functions that we are gonna explore in the upcoming series. So the website is basically have a lot of features. For example, this view tab, you can get a lot of features in this view tab, in the run tab, in the kernel tab. We have not started the notebook, so let me start the notebook first. This is a Kotlin notebook. This supports the Kotlin programming languages, and a lot of additional features as well. So over here, if you can see, we got a presentation mode. We can show line for us. It can collapse the cells for us, and in kernels we can also change the kernel settings. We can interrupt the settings, and in settings we do have something as themes. For example, most of the coders are like, okay, we don't prefer light theme, we want dark theme, or we want solarized theme. So we have customized it for them, and it works fast. Number one thing, that's what we all coders want. We want our code to get executed as fast as we can. So that's the brilliance of this platform. And we do have this extension where once we enable it, okay, once we enable it, we get a lot of different kinds of extension that we can discover, such as we do have something as Git. If you just search for Git, you get something as the Git extension. Here's a Git library that we can use in this S2 platform. There are many such things into this platform. This is the hierarchy of it. Wherever the code comes along, it will get saved over here. You can download it. You can download this files as a PDF or any kind of format that you want. Also, it has markdown, it has raw, and it has many more functionalities that we are gonna explore in the upcoming videos. Okay, so now let's start with implementation of this vectors. How about whatever we discussed in the theoretical aspects, like getting the distance of a vector from the origin? Nothing. So now let's start with implementing the aspects of the vectors. As we thought, come on. So now let's start on implementing the practical aspects of the vector. So whatever we discussed in the theoretical concepts, let's implement it. For example, when we discussed finding a distance of a vector from the origin, it is nothing but a norm of a vector. So now let's start by defining a vector and finding its norm, then getting the components of the vector and then calculating the norms. Okay, so the first magic line that we are gonna use is %use s2. This one magic line will automatically make every math library happen to us. So now let's start with it. So this is how we implement the s2 library, just by one line of command. Once it gets executed, we can just use the dense vector. Dense vector is nothing but a real vector where the most value are non-zeros. So where v is equal to dense vector. Okay, I miss vector. So this is how we create a dense vector. If we print it, we will get a vector in a way of this. So now let's get the components of the vector. So we will use the command val x is equal to v1 dot get the first item, the first component, that is 3, and val for y-axis we will get second component. Once we get it, now it's time to calculate the norm. So as discussed in the theoretical videos, the formula is under root of x square plus y square. So that's we're going to implement it. Power is nothing but raised to. And we want it under root, so 0.5. So when we print the norm, yeah, we got the norm. We got the length of the vector for the components 3, 4. 3 on the x-axis and 4 on the y-axis. 3 being the first component and 4 being the second component. Okay, so as we have performed this vector operations of getting a norm of a vector from the origin to a particular vector, so now let's move on to the basic operations of a vector. So we are gonna do some vector addition, vector subtraction, and vector multiplication. So for that we must need another vector. So let's do vector where w is equal to the dense vector, well it will be the So we have declared another vector. So now let's add the vector v with vector w and store it into the variable name vec addition. Now let's print it. So we got the added vector. If you can see, 3 plus 2 is 5 and 4 plus 5 is 9. Now let's move on to the vector subtraction. It is nothing but vec sub Yeah, so this is the subtraction of a vector. Now let's move on to the multiplication of a scalar with a vector. So for that we must declare a dense vector. Let's give the vector name as x. And this is a scalar that we are giving the value as 2, which we will be multiplying with the dense vector x. Now to multiply it, we will just do val b is equal to x dot scaled s, and when we print b, we will get the scalar multiplication. As you can see, 2 into 2 is 4 and 2 into 1 is 2. This is how the scalar multiplication works. So that's it for today. We have covered a lot of theoretical concepts on vectors, and also did a little bit of hands-on on vectors. This is just a base, not even a base. Think it of as a prerequisite to get our series and the journey of the knowledge started. In the upcoming lectures, we are going to discuss about algorithm matrices and slowly, steadily go into data science and learn a complex algorithms, do some real world case studies. The series will go as like we will cover the theoretical aspects, because theory is as important as practical. If you don't know the theoretical concepts of how the pieces are getting joined together, even if you are a good coder, you must know where this matrices, where these concepts are getting implemented in the data science. So that's why we will cover the theory section in the first half of the video, and then later jump on to the practical session. That's it from my end. Thank you. Make sure you watch our new videos and subscribe for us. Thank you.